Okay, in this slideshow, I want to show you how to prove stuff. And so often students shy away from this, but I think that in this set of slides, I'm going to give you some basic tools that you can use, some basic things that you can remember. And once you build your toolbox, you should be well on your way to being a great mathematician and proving all kinds of theorems. So we have to change our perception of how we think of mathematical proofs. And typically, this is how we think of mathematical proofs. And so this is how we want to start thinking about them. Sexy, right? So all right, so what's some of the things in our toolbox that we have? Well, the first thing is we have something called an axiom. An axiom is just a logical statement that's assumed to be true. So an example of an axiom would be for real numbers, there exists a zero such that x plus 0 is x. So this is a statement that we assume to be true. It's a building block. It's like a rule to our game. So in our toolbox, we also have definitions. And a definition is a precise description of a mathematical term. And so an example of this would be for an m by n matrix A and x and Rn, A times x is a linear combination of the columns of A with the components of x as its weights. So this is a definition. This is fixed. It's a precise description of a mathematical term. So the last thing that we're going to put in our toolbox are theorems. And theorems are mathematical statement that is proved using vigorous reasoning. So the difference between an axiom and a definition and a theorem is that axioms are given to us. They're just rules of the game. Definitions are mathematical descriptions, and theorems are mathematical statements that have to be proven using vigorous reasoning. So an example of a theorem is if A is an m by n matrix and U and V are in Rn and C is a scalar, then first A, we have that A times a quantity U plus V is equal to A times U plus A times V, which says basically that that matrix A distributes across the vector sum. And B, A times Cu, where C is a scalar and U is a vector in Rn, is equal to C times AU. And that portion of the theorem basically says that the constant or scalar C can be factored to the front. So let's look at a theorem and see how we might prove this, or a statement, let's say, and see how we prove it. Let the set S be equal to vectors v1 to vn. We like to prove that if x and y are in the span of S, then x plus y is in the span of S. So we just need to recall that being in the span of a set S means that we're a linear combination of the vectors in that set. So this statement is saying that we want to prove that if x and y are in the span of S, which means that x and y both are linear combinations of v1 to vn, then their sum, the vector that is their sum, x plus y, is also in the span of S. So the first thing we need to consider is what is given to us. So we've been given that the set S and the fact that x and y are in the span of S. So we're given this set S, which is v1 to vn, and we're given the fact that both x and y are in the span of S, which means that x and y are both linear combinations of those vectors in S. And we must show that the sum x plus y is also in the span of S. So as I start any proof, the first thing I'm going to do is write down the given information, which I've done here, namely that I have a set S and x and y are in the span of S, and I'm going to write down what I must show. And in this case, I must show that x plus y is in the span of S. And for each of my proofs, I'm always going to have these two statements at the top, because it helps me remember what I have to use in order to get my proof done, along with axioms, theorems, and definitions. And it also reminds me of what I'm actually trying to show. So the one caveat we want to make sure that we have here is that we need to be careful not to use any part of what we must show in our proofs. So we have to be careful. We have to show here that x plus y is in the span of S. So at no time while we're doing our proof can we already assume that x plus y is in the span of S. All right, so as I begin my proof, we know that both x and y are in the span of S. So what does this mean mathematically? Well, it means that there's some linear combination of the vectors v v2 to vn that equal x, and I have that x is equal to c1 v1 plus c2 v2 all the way up to cn vn. And we also know that there's a linear combination of those vectors that equals y, namely new scalars d1 v1 plus d2 v2 up to dn vn equals y. Then if we add x and y together, because that would be their sum, and we're interested in their sum, we say that simply means we need to add those scalars. So c1 plus d1 v1 plus c2 plus d2 v2 all the way up to cn plus dn vn would be equal to the sum of those two vectors x and y. Now if we just let k1 be c1 plus d1 and k2 be c2 plus d2 and so on and so forth all the way up to kn is equal to cn plus dn, then we see that x plus y is equal to k1 v1 plus k2 v2 all the way up to plus kn vn. Now what does that mean? Well, that means that x plus y is a linear combination of the vectors in S, and therefore the sum of x plus y is in the span of S. So I've proven that if x and y are in the span of S, then their sum, x plus y, is also in the span of S. So here's another statement that I like to prove. So I want to prove that if u plus v equals u plus w, then v equals w. And want to assume that u, v, and w are real numbers. And we could do this if they were vectors in Rn, but in this case, these are real numbers. So we have some axioms available to us for the real numbers, and those are the 10 axioms that we're supposed to remember. And so what is given to us? We're given that u plus v equals u plus w, and that u, v, and w are real numbers. And so we can therefore use any of the properties of real numbers we need because we were told they were real numbers. So those 10 axioms are available to us. And what must we show? Well, we must show that v is then equal to w. So this is something we use in real numbers all the time, right? That if u plus v equals u plus w, we all assume that v must be equal to w. And so what we want to do is rigorously prove that here. So for our proof, we know that u plus minus u plus v equals u plus minus u plus w, because one of the axioms says that since u is a real number, u must have its additive inverse, which is minus u, so I can add that to both sides of the equation. And then we know that u plus minus u equals 0, because there's an additive identity, which is, there is u plus minus u is equal to 0. That's one of our properties. And so then we have 0 plus v equals 0 plus w. And 0 is in essence the mirror for real numbers. And so therefore v equals w. So in summary, we want to clearly state what is given. You want to clearly state what you must prove, so these should always be included in a good proof. And then you need to substantiate your conclusions with axioms, definitions, and/or theorems.